Express 2 cos theta minus sine theta in the form of r cos theta plus alpha, where r is positive, alpha is between 0 and pi over 2, give the exact value of r, and the value of alpha in radians to 3 dp. Okay, so this is pretty standard stuff. So the r cos theta plus alpha we can rewrite as r cos theta cos alpha minus r sine theta sine alpha. And we're setting this equal to 2 cos theta minus sine theta. So if these two things are to be equal, well, we can first of all see we have cos here, cos theta there, cos theta here. We have sine theta here, sine theta here. So for them to be equal, the r cos alpha should equal to 2, and the r sine alpha should equal to, I'll put a 1 here, should equal to the 1. So writing that out, we have r cos alpha is 2, and r sine alpha is 1. We can divide the two things. So r sine alpha over r cos alpha is equal to 1 over 2. That's doing the entire purple equation over the blue equation. The left-hand side, the r's cancel. We're left with tan alpha is a half, inverse tan of a half, and we get 0.464. And to get r, we can just do the square root of this 2 squared plus the 1 squared that we have there. 2 squared plus 1 squared is equal to root 5. So then 2 cos theta minus sine theta would then be equal to root 5 cos theta plus alpha, where alpha is 0.464. And that's part A. So for part B, we have all this text over here, so let's just get through that. Figure 6 shows the cross-section of a water wheel. So here is our water wheel. Point P is at the end of one of the paddles, as shown in figure 6. The water level is horizontal and at constant height, that's what we assume. The vertical height of h, meters, so h is in meters, let's highlight that now. The height h of P above the water level is modeled by this equation here, where t is time in seconds after the wheel starts rotating. Use the model to find the maximum height of P above the water level in part 1. For part 2, we want to work out the value of t when this maximum height first occurs. Alright, so let's start with B part 1. We want to work out the maximum height of P above the water level. So we can rewrite our equation. So what we have over here, the 4 cos of 0.5t minus 2 sine of 0.5t, is pretty much the same as what we have here. But it's off by a factor of 2. So here we have 4 cos, here we have 2 cos, minus 2 sine, just minus 1 sine. So this is 2 times bigger, and also the theta that we have over here has been replaced with 0.5t. So if we times both sides of this equation by 2, if we replace the thetas with 0.5t, then this would be equal to what we have here. So we can re-express this as then what we have here with the extra 2 and the theta being 0.5t. So plus 2 root 5 cos 0.5t plus 0.464. We want to find the maximum height. The maximum height would be when, if we think of this cos function that we have over here, cos goes between 1 and minus 1. So to make height as big as possible, we want cos to be as big as possible. So cos would be 1. That would give us with a maximum height, I'll just write that as h max as 3 plus 2 root 5 times 1 meters. And for part 2, we want to work out the time when this maximum height occurs. Well, again, we set the cos to be equal to 1 to get that maximum height. So we can set this equal to 1, solve that. So 0.5t plus 0.464 is equal to inverse cos of 1, which is either 0 or 2 pi or 4 pi, etc. If we then, for these 3 values that we have here, take away 0.464, divide by the 0.5, we end up with minus 0.464 928, 11.64, 24.20, and time has to be positive. We're looking for the first time when this maximum height occurs. The first time when this occurs would therefore be 11.64. Can't be this because that's negative, so the first time would be 11.6 to 1 decimal place. We want it to 1 dp. Part C. In a single revolution of the wheel, P is below the water level for a total of t seconds. According to the model, find the value of t, giving your answer to 3 sig figs. Alright, so we're trying to work out time t. Time t is the time for which P, which is this point over here, is beneath the water level. So as you can imagine, the wheel rotates, P is going around like this, eventually P hits the surface of the water, it then dips beneath the water level, hits the water surface again. We're looking for that time there. So what we want to do is we want to work out the times using the equation for height that we have over here, set that equal to 0, set h equal to 0. That will be when P is at the surface of the water. Once we have those times, find the difference between them, and we will get one of two things. We'll get either the time beneath the water level or above the water level. And then we have to distinguish which one would be beneath, which one would be above. But again, first thing, work out the times at which P is at the water level. So when h is equal to 0, so part C, we're setting h to be 0. H is equal to 3 plus 2 root 5 cos 0.5t plus 0.464. That's the equation that we got in B part 1. We're setting this equal to 0. So cos of 0.5t plus 0.464 is equal to, rearranging this, take away 3 from both sides. So this 3 here, take that away, then divide by the 2 root 5. So minus 3 over 2 root 5. Do inverse cos of that. And we end up with 2.3061 for our first value. It's a cos graph, so do 2 pi minus that to get our second value. That would be 3.9771. And then we can add 2 pi to either of these values to get our next values, because a cos graph repeats every 2 pi. So add 2 pi to this, we get 8.5893. Now we can rearrange for t, so we can, with these 3 values here, take away the 0.64 and then divide by 0.5. And if we do that to those 3 values, we end up with 3.6842, 7.0261, and 16.2506. So what we've worked out here, again, are the times when point P is at the water level. So when point P is here or here, it's not the time that it takes to go from one point to another, it's just the times when it is at the water level. So if we work out the difference between these times here, let's call that delta t. If we work out the difference, that will tell us the time either when P is above or below the water level. So for the first 2 times, so this one and this one, if we find the difference between them, we end up with 3.342 seconds. And if we find the difference between these 2 times here, we end up with 9.224 seconds. Now the reason I've worked out both is because if we had just worked out one, we don't know if that's the time above or beneath the water level. Now that we have both times, one of these must be above, one of these must be below, and by looking at the diagram, we can see that the time spent below the water level must be shorter than the time spent above, assuming this wheel is rotating at a uniform speed, which it is. So therefore we must be picking the shorter time. That would be the 3.34, so that would be our answer to part C. 3.34 seconds. And for part D, in reality, the water level may not be of a constant height. Explain how the equation of the model should be refined to take this into account. So let's look at the equation of our model. It's what we have over here. So there are various transformations that have been applied to a cos graph to make it what we have here. we have a horizontal stretch, a horizontal translation, a vertical stretch, and a vertical translation. Now we're looking at the water level, so if the water level is changing, that would affect the height above the water level. So we're just considering the vertical transformations here. We're not going to be worrying about the 0.5 or the 0.464. So let's think about how this graph represents the scenario that we have over here. I'll start by just thinking about a normal cos graph. So let's say we have h is equal to cos t. H represents the height above the water level. So if we just had h is equal to cos t, that would be a regular cos graph which is centered about the water level like this, where the height of that would be 1. If we then multiply everything by 2 root 5, we have 2 root 5 over here. That's a vertical stretch, scale factor 2 root 5. Our graph, again, rough sketch, would look something like this. So a bit taller now. This would be 2 root 5. The plus 3 that we have here will shift everything up 3 places. So our graph would then look something like this. So it doesn't matter where we start from horizontally. We're not interested in the horizontal transformations. It would look something like this, where if I draw a line through this central point here, this distance from the top of the wheel to that central point is 2 root 5. This distance from the central point to the bottom of the wheel is also 2 root 5. And this central line that we have has been shifted up 3 places. So basically, this distance here is 3 meters. So the 3 meters represents the distance that the center of the wheel is above that water level. If the water level is changing, that means this 3 is also changing. And that could change for various reasons. It could be, for instance, tide, so as the water comes in and out. It could also be because of rainfall, if this water wheel is on a river. So it could be for various reasons. So that 3 would need to vary. It would likely need to be some kind of function of time. That would be our answer for Part D. Part D is asking us to explain how we would refine the model to take into account the changing height of the water level. So change the 3, make it some kind of function of time.